Welcome to Phase 1, Lesson 1. Containers. The mental model. This is the big one, the idea that made modern software possible. And I want you to really get it, because every future lesson, Kubernetes, Argo CD, everything, is built on top of this one insight. You have felt this as a beginner, I promise. It works on my machine. You build something, it works. You send it to a friend, broken. Different operating system, different Python version, missing library, different settings. The app and its environment got separated, and the app cannot live without its environment. The container insight. Bundle the app and its entire environment, code, runtime, libraries, config, even the operating system's users and file system layout, into one portable package. When you ship that package, it runs the same everywhere because it carries its whole world with it. This is where almost every beginner builds the wrong picture. Let me fix it now, because the wrong picture will sabotage you later. A container is not a mini virtual machine. A virtual machine simulates an entire computer. It has its own kernel, the core of an operating system, and its own virtual hardware. That makes it heavy, slow to start, with gigabytes of overhead. A container, on the other hand, is a process, just a running program, like any program on your computer, but locked in a box. Here's the picture. Your laptop has one Linux kernel. On top of it, many containers run side by side. Container 1 runs app 1. Container 2 runs app 2. Container 3 runs app 3. Each has its own files, its own network. The isolation comes from two Linux features, Namespaces and Cgroups. Isolation comes from two Linux features. First, Namespaces. Namespaces control what a process is allowed to see. Its own file system, its own network, its own process list. A container inside a namespace literally cannot see anything outside its box. The second feature is Cgroups. Groups control how much a process is allowed to use. CPU, memory, disk. If one container goes crazy and tries to eat all the memory, the group limits stop it from taking down your whole laptop. Because containers are just processes, they start in milliseconds and use only what they need. You can run dozens on one laptop. And when you get to Kubernetes, everything Kubernetes does is manage these boxes. Which containers exist, where, and how many. Here is the second mental model. Images versus containers. Two different things, always confused. An image is the blueprint. A frozen snapshot of everything needed to run the app. It is read-only. It is a file you can share, store, and download. A container is the running instance. Created from an image, alive right now, with its own writable layer. The classic analogy. An image is a recipe. A container is a cake you baked from it. You can bake 100 cakes from one recipe. Each cake is separate, running, mutable, and eventually eaten, meaning deleted. A container's writable layer is temporary by design. Stop the container, and all its changes vanish. That is why, how do I save data, is Lesson 2 topic. That is where volumes come in. Time to touch 1. Install Docker Desktop from docker.com. Download for Windows. It will ask you to enable the WSL2 backend. Say yes. It needs a login, a free account. Give it a minute to start. The whale icon should stop animating. If you hit any install snags, tell me the exact error. This is Docker on Windows, a rite of passage, and we will debug it together. Now open your WSL Ubuntu terminal and run this command. Docker run -d -p8080:80 -name mine Jinx. Let me unpack every piece, because each one is load-bearing. Docker run creates a container from an image and starts it. The -d flag means detached. Run it in the background. Do not hold my terminal. -p 8080 to 80 maps port 8080 on your machine to port 80 inside the container, where Jinx listens. Your machine, 8080. Container, 80. -name mine Jinx gives it a name so you can talk to it. And Jinx is the image to use. Docker downloaded it from Docker Hub, the public image registry. Now check it as alive. Run Docker PS. This lists running containers, just like PS lists processes. See the theme. You should see your mine Jinx container, with the image Jinx, status up, and the port mapping 0.0.0.0 to 8080 to 80. Now open your browser and go to localhost. Port 8080. That is Jinx welcome page, being served by a program running inside a box on your laptop. That is your first real container in action. Now get inside the box. Run docker exec -it -jinx bash. You are now inside the container. It looks like a Linux box, but look closer. Run ps auxiliary notice. These are not your laptop's processes. It has its own process tree. Run ls/, its own file system built for this image. And cat /etc/os release to see the operating system. Then type exit to leave. Look closely. PSAUX shows only the processes inside the container, not your laptop. ls/ shows a file system built just for this image. This is your first hands-on proof of the mental model. A container is a process with its own view of the world. When you type exit, you leave the container, but it keeps running because it was detached. Here is your exercise. Run the Jinx container exactly as shown. Open localhost 8080 and confirm the welcome page. Read the Docker PS output. What is the image? What is the status? What ports are mapped? Get inside with docker exec, run PSAUX and ls, then exit. Then create a second container from the same image, docker run -d, -p8081 to 80, -name my, Jinx, 2, Jinx. Open localhost 8081. 2 cakes, 1 recipe. Then stop 1 with docker stop my, Jinx, 2. Check docker ps, and notice docker ps - shows it stopped, because it still exists, just not running. Finally clean up with docker rm my, Jinx, 2. Let us recap. A container is a process, locked in a box. It sees its own file system, its own network, its own processes, thanks to namespaces. It uses only what it is allowed, thanks to Cgroups. An image is the blueprint. A container is the running instance. And when you get to Kubernetes, everything it does is manage these boxes. You have the foundation now. Great work.